Hi class, this is Dr. O'Connor. In this video, I'm going to talk about oxidation-reduction reactions. So what is an oxidation-reduction reaction? By the way, they're also called redox reactions. And these are reactions in which electrons transfer from one atom to another atom. Oxidation is defined as the loss of one or more electrons by an atom, an increase in charge, or a gain of oxygen atoms. Reduction is the opposite, a gain of one or more electrons by an atom. You can look at it as a decrease in charge or a loss of oxygen atoms. It turns out that many biological reactions are oxidation-reduction reactions. So much of the energy that's produced in cells are the result of redox reactions. Redox reactions, the electrons lost from oxidation are gained in reduction. And I'll tell you right now, oxidation and reduction occur simultaneously. You cannot have one without the other. So how do we know which one occurs? Well, here we have this arrow. This is oxidation, and this arrow pointing to the left is reduction. So for example, in this case here, I look at this charge here, a -2. On this side, it is a -1. The charge has increased. So therefore, we have oxidation. Here again, we have a -1 and here a 0 charge. Again, an increase, oxidation. If I look at the reaction going this way, here we've gone from a -1 to a -2, so in this case we have reduction. I think the best way to look at these is to actually look at some real examples. So as far as the reactant goes, it can be anything. It can be a neutral atom, a monatomic ion like sodium ion or iron 3 ion, a polyatomic ion like, for example, carbonate ion, or a molecule, for example, methane. As I said, oxidation and reduction always occur together. Now, let's talk a little bit about reducing agents and oxidizing agents. I'll tell you right now, the reducing agent is the substance that is oxidized, and the oxidizing agent is the substance that's been reduced. So a reducing agent is going to lose one or more electrons. It's what causes reduction, and it itself undergoes oxidation. In other words, it becomes more positive, whereas an oxidizing agent gains one or more electrons. It causes oxidation. It is the substance that undergoes reduction, and you can think of it as becoming more negative or less positive. So let's take a look at this reaction here. If I take a piece of copper wire and if I put that into an aqueous silver nitrate solution, here's what's going to happen. After some time, what we'll see is the solution is going to turn blue, and we're going to see silver-like icicles deposit on the piece of copper, almost like a Christmas tree with tinsel. So here's what's happening. We have solid copper, and remember, aqueous silver nitrate looks like this. We have silver and nitrate ions, right? And so we have our copper solid, we have silver ions, and what happens is we end up with the solid copper loses 2 electrons to become copper ion, and those 2 electrons actually go to 2 silver ions, so that the silver becomes solid silver. That's what's depositing here on the copper wire, is solid silver. So let's take a look here at what happens. Solid copper has a 0 charge. Silver ion has a +1 charge. Copper ion has a +2 charge. And here, silver metal has a 0 charge. So we see that for 2 silver ions, okay, an electrons have been gained in order to form the solid silver. So that means that silver ion was reduced. In this case here, we have copper, solid copper, and it loses 2 electrons to become copper ion. Therefore, copper, solid copper, has been oxidized. And it turns out that solid copper is the reducing agent and silver ion is the oxidizing agent. It causes the oxidation. Electron donors, like metals, are the most powerful reducing agents, and we can predict it by ionization energy. So we know that ionization energy will increase as we go across a period. And it turns out that the greater the ionization energy, the less reducing power that the metal has. So the better reducing agents are towards the left-hand side of the periodic table. Electron acceptors, like for example your nonmetals, are the most powerful oxidizing agents, and that can be predicted by electron affinity. Some applications of redox reactions or oxidation reduction, corrosion. Think about the rusting of a car. When a car is exposed to air, the oxygen in the air, what happens is you've got the iron metal, right, which becomes oxidized to rust. Combustion reactions, when we burn, for example, propane, when we grill our food, then we burn that propane by oxidation with oxygen, and the oxygen comes from the air. Respiration, this is the process of breathing and using oxygen for biological redox reactions. We're going to learn all about those next semester. Bleaching, so if you get your hair bleached or when you clean your clothes, those are redox reactions. And then metallurgy, which is the extraction and purification of metals from their ores. So there are a lot of applications of redox reactions. And again, all of the reactions, or many of the reactions in our cells, are redox reactions. So in order to determine what has been oxidized or reduced, we need to define the oxidation number, and this is a number that indicates whether an element is electron-rich, electron-poor, or neutral. So here are some rules that we need to know. Any atom in its elemental state has an oxidation number of 0. So for example, hydrogen gas, its oxidation number would be 0. Mercury would be 0. Solid copper, 0. Monatomic ions have oxidation numbers equal to their charge. So calcium ion, it has an oxidation number of +2. Sodium ion, a +1. Chloride ion, a -1, and so on. Now, when it comes to molecules, it's a little different because, remember, there are no charges. So what we do is we will treat the atoms as if they were monatomic ions. For example, hydrogen is almost always a +1 oxidation number, and oxygen is almost always a -2. There are some exceptions. When we have compounds with more than one nonmetal, the most electronegative atom is going to have a negative oxidation number, and the least electronegative will have a positive oxidation number. Okay, so we can see right here, we've already been told that hydrogen is always a +1 and oxygen is usually a -2. And notice here in these compounds in water here, the oxidation numbers add up to 0. These are neutral molecules. Look at ammonia. The oxidation number for each of the hydrogens is a +3. Nitrogen would be a -3. these add to 0. Here for sulfur and oxygen compound, the oxygen is more electronegative than the sulfur. Therefore, we already know oxygen has a -2 charge. So the two -2's add up to a -4. So what plus a -4 will add to 0? The sulfur must be a +4. Here we have the carbon and the two oxygens. We know that the oxygens are a -2. Those add to a -4. So again, the carbon would be a +4. As I said before, the sum of oxidation numbers must be 0 for a neutral compound. Sum of oxidation numbers must add to the charge on a polyatomic ion. Let's do a few examples. Here we're told to assign oxidation numbers to each metal in the following compounds. Well, what do we know? This is an ionic compound, so we know that the atoms would have the same oxidation number as the charge. In this case, we have a +4 for the tin and a -1 for the chlorine. Here we have copper nitrate, and we know that the copper has an oxidation number of a +2. Again, it's just the charge on the ion. Okay, let's assign oxidation numbers to each atom in these compounds. We know that hydrogen is always a +1, and we know oxygen is a -2. Now remember, here we have to determine the oxidation number of the chlorine. It can have an oxidation number of, anywhere from, a -1 to a +7. So we have 4 oxygens, so -2 times 4, and we have 1 hydrogen. So a -8 plus 1 is a -7. So what plus a -7 is equal to 0? A +7. So the chlorine would have an oxidation number of a +7. Let's take a look at this ion here, permanganate ion. Remember, in this case, all of the oxidation numbers must add up to the charge, in this case, a -1. Again, I have a -2 on the oxygen, and there are 4 of those, so 4 times a -2 is a -8. So a -8 plus what will equal a -1? So that would be a -8 plus a +7. So the manganese would have a +7. Let's take a look at this compound. I want to know the oxidation number of the chromium. We know oxygen is a -2, potassium is a +1. Remember, all of our oxidation numbers have to add up to 0 for a neutral compound. I have 2 of these potassiums, so I have a +2. I have 7 of these oxygens, so that'd be a -14 plus 2 would be a -12. So a -12 plus what equals 0? That'd be a +12. The oxidation number of the chromium is not a +12. We have 2 of them. So the 12 divided by 2 would be a +6 for the chromium. So the oxidation numbers here are a +1 for potassium, +6 for chromium, and a -2 for the oxygen atom. Just practice some of those. Your book has a nice setup as far as how to do these. We're given some reactions, and we're asked to identify the atoms that are being oxidized and reduced. Okay, well, I know that calcium, in its solid state, has an oxidation number of 0. Chlorine, an oxidation number of 0. But in the compound calcium chloride, calcium has an oxidation number of a +2, same as the charge, and chlorine a -1. So what's happened here is calcium has gone from a 0 to a +2. It's increased in charge. Therefore, calcium has been oxidized. And in this case, our chlorine has gone from 0 to a -1. The charge has decreased. Therefore, diatomic chlorine has been reduced. And calcium is the reducing agent, where chlorine is the oxidizing agent. Here we have two magnesiums, carbon dioxide, to produce magnesium oxide and solid carbon. So here, solid magnesium, it's an elemental state that has an oxidation number of 0. We just have to check each atom. We know here for carbon dioxide, oxygen has an oxidation number of a -2. And in this case, the carbon would have an oxidation number of a +4, because there are two of those oxygens, so oxygen a -2. Here in the compound magnesium oxide, magnesium has an oxidation number of a +2, oxygen is a -2, and of course solid carbon, that has an oxidation number of 0. So let's see what's going on here. Magnesium has gone from a 0 to a +2, an increase in charge, so the magnesium has been oxidized. Notice the oxygen is always a -2, so nothing's happened with the oxygen. But here we have carbon going from a +4 to 0, so that's a decrease in charge, therefore, or a decrease in oxidation number, I should say. Therefore, carbon dioxide has been reduced. Okay? So carbon dioxide acted as our oxidizing agent, magnesium solid acted as our reducing agent. Let's take a look at this one. Here we have a combustion reaction. We have methane and oxygen to produce carbon dioxide and water. The oxidation number of hydrogen here is a +1, and the oxidation number of the carbon would be a -4. Okay, our oxygen here is a 0, and here oxygen is a -2, same here. Hydrogen is a +1, and let's see, we have carbon here would be a +4. So carbon has gone from a -4 to a +4, and so therefore the charge has increased. It has been, methane has been oxidized. Oxygen goes from a 0 to a -2, the charge is decreased, so O2 has been reduced. Okay, so that means O2 acted as an oxidizing agent, methane acted as a reducing agent. Okay, so be able to do that, be able to look at a reaction, determine what's been reduced, what's been oxidized, which acts as the reducing agent, and which is the oxidizing agent. So now we're asked to identify the following reactions as redox, precipitation, or neutralization. Sometimes you can have one that can be more than one type of reaction. So let's take a look here. We already know this one, sorry. This one we did. This one here is a precipitation. And we know it is because we have two ionic compounds mixed together to produce a solid, and then we have this aqueous sodium chloride. This one here, well, what do we have here? Potassium hydroxide, hydrochloric acid. Oh, we have a salt and water. This is a neutralization, acid-base neutralization. And then this one here, we have iron 3 oxide, we have solid carbon. Here we have solid iron and carbon dioxide. Anytime I see something in elemental state on one side of the equation, then I'm pretty sure it's a redox. But here I know it is. Here I have iron 3 oxide. Iron has a +3 oxidation number. Here it has 0. So in this case here, we've gone from +3 to 0, a decrease. So the iron 3 oxide has been reduced. The carbon here in its elemental state is 0. And here, the carbon is a +4. We've gone from 0 to +4, increase in charge. The carbon has been oxidized. In this case, our iron 2 oxide has been reduced. So the iron 3 oxide acts as an oxidizing agent, and the carbon acts as the reducing agent. So anyway, that's it. That concludes chapter 4. If you have any questions, make sure you contact me. Everybody have a great evening.